So what we're going to look at is the definition of the integral. In high school mathematics, you generally get introduced to this idea of the integral as a way of finding the area underneath a curve. And somewhere along the lines, you get told a story about how it's the sum of rectangles with really, really small width. And if you just add up all those rectangles, you get you get the area underneath the curve. What we're going to do today is put that idea to the test a bit more rigorously and explain exactly what the definition of the integral is. And here it is in all its glory. Let's explain. So what we would say is that the integral from a to b of some function f of x dx is equal to the limit as n approaches infinity of f of the sum of f of a plus 1 I multiplied by delta x from I equals 1 to I equals n, where delta x equals b minus a on n. So that's a mouthful if I've ever heard one. Ever heard it. And what we're going to try and do is make some sense of it, because why not? That's what maths is all about. So first thing we can say is this. Let's break down a few ideas here. This delta x is b minus a on n. So if we've got some function here, f of x in pink, and we say the left part here is a and the right part here is b, then delta x is the width of a rectangle if we have n rectangles. And even that idea can be quite tricky, but b minus a, you would agree, is the length, is the distance between a and b. Let's say that n was 2. So b minus a on 2 would give us the halfway point, and then we'd have one rectangle here. In fact, I can do that. One rectangle here and then one rectangle here. So if n was 2, b minus a on n would be the width of a rectangle. B minus a on n. B minus a on 2 would be the width of this rectangle. If we made it 3 rectangles, b minus a on 3 would be the width of one of these rectangles, right? So that's probably the first key idea that we need to keep in mind. Okay, the next thing we're going to say is we're going to look at this thing inside here, which is challenging in itself. It says a plus I multiplied by delta x. Okay, what we're going to say about that is like the position. Okay, and I'm going to explain this in more detail in a moment, but just keep that idea in mind that a plus I times delta x basically tells you where the x value, where along the x-axis you're going to evaluate the height of the function, because we're taking f of that value. So it's going to tell you where, for which x value, you're going to take the height of the function. Okay, so we'll come back to that in a moment. What I like to do in terms of my own understanding is to pick some values of n. Obviously, n is approaching infinity at some stage, but before it gets to infinity, it has to go through 1, 2, 3, 4. And so for me to understand this personally, I find it useful to just pick n being small numbers to sort of see what's going on. So let's try that. Let's set n to be equal to 1. So this right-hand side, if n is equal to 1, it's going to look something like this. And just ignore this first part for now. I just want to look at this delta x. If n is 1, then we get delta x being b minus a divided by 1, which is just b minus a. Remember, n is the number of rectangles we have. So the width of this rectangle will just turn out to be b minus a, right? So we can say when n is 1, delta x is b minus a. Okay. And then we get this situation here. Let's have a look at all this. We're saying f of a plus delta x. We need to evaluate the function at a plus delta x. Well, delta x is b minus a. So a plus b minus a. Now I'm going to say that again. A plus b minus a is just b. So this turns out to be f of b. And that should make sense, right? We've got one rectangle, and the height of that rectangle has a height of f of b. And then to define the area of this one rectangle, we have to multiply f of b, which is the height of the rectangle, by delta x, which is b minus a, which is the width of the rectangle, yeah? So hopefully that sort of logic, you can see where that sort of comes from, right? So that's when we have one rectangle. Okay, hopefully you can start to think what's going to happen from here. We're going to take, let's say n equals 2 now, and let's really step this through. So n is 2. So what we're going to say is if n is 2, that means we've got two rectangles. And so again, let's start at the right-hand side here. Delta x is going to be the width of the rectangle. Width of each rectangle, right? So b minus a again is the total width, but now we've got two rectangles. So b minus a on 2 is the width of one rectangle, yeah? So that's the width of one rectangle. So delta x is different, right? When n is 2, it's b minus a on 2. Okay, and then what we have is, this is where it gets a little bit tricky. We need to sum, basically you would agree we need to sum this rectangle with this rectangle, right? So what we need to do is we need to take, all right, f of a plus I times delta x. Okay, again, this is the position. Okay, so if we take a is this point here, plus, all right, let's set I to be 1. A plus delta x. Remember, delta x is the width of the rectangle. So a plus delta x gets us to this position here, right? It's going to be halfway. So this is going to be the height of the rectangle at f of a plus 1 times delta x. So that's here. That's the halfway point. So let me show you what the sort of final line is here. So that's this first part, right? So we take a plus delta x. That I is a 1 in the first instance, okay? Because we've moved from a, we've moved one group of delta x across, okay? And then in the second instance, we're going to move two groups of delta x across from a. So then we're at f of a plus 2 times delta x. So we start at a plus two groups of delta x gets us to here, which is at b in this instance. And so yeah, we get the height of the function at that point is f of a plus 2 delta x multiplied by delta x again, which is the width of the rectangle. So again, hopefully you can see how this corresponds. This first part corresponds to the area of this rectangle. This second part corresponds to the area of this rectangle. And then obviously not going to do 3, and we obviously can't go up to infinity, but I'm hoping you can see that you could just follow the same process, right? You just sum all of these rectangles together. And what we're saying is now this idea of limit, the limit as n approaches infinity, as we have more and more and more rectangles. And I have a cool animation here. I think it's cool. N just gets larger and larger and larger. You get the idea. This becomes a better and better and better, keeps getting better approximation of the area underneath the curve f of x. So pretty cool, huh? If you understood that, you're doing very well. It's quite a challenging idea. So good luck with all your studies, and I'll see you soon.